So model 3, which is a logistic equation, and you have seen this equation now a lot. It's a famous one, which is the one that describes the growth of population like flu population, okay? The contaminated people. And you have heard about exponential growth. You have heard about how to stabilize, how to flatten the curve. Now these words are like very famous in the community. And the logistic equation, so I have a logistic model describe the growth of population, okay, in a closed environment. It's given by dp dt equal rp. This is from before, it's growth, but I have minus gamma p squared. Okay, so dp dt equal rp is closed environment without hunting, without anything, and now I have a rate that of how it's decreasing, that it depends on the square of the population. So imagine you have a population, so forget about the virus, okay? So imagine you have a population in a closed environment, so they will be growing up until I have scare of resources. When I have scare of resources, then the animal will start fighting together, and then the population will decrease, and by minus gamma p squared. Until there is stability in the, well, until there's enough food for everyone, then the population will increase, but then when there's scarce of population, then the population will start fighting, and then we will have a decrease in the population. This is a minus gamma p squared. Some other way to describe it, or simply you can write dp dt as r p times 1 minus p over k. It's a different way to, okay. Since I'm talking about populations, this is p of t, and t is positive, okay? So t is positive, and I'm imagining that p of t is also positive, just for the sake of the model. So let's analyze the thing. Now what are my equilibrium solution here? My equilibrium solution are, this is p as a function of t. My equilibrium solution are p equals 0, remember, I want the right hand side to be 0, p equals 0, and p equal k. But I will not draw the direction field. I will just tell you how I will just do the qualitative measure. Okay, so qualitatively, let's draw p prime in terms of p. So remember, p prime equal rp into 1 minus p over k. This is a parabola passing through 0 and k, and the maximum is k over 2, is attained at k over 2, and this will be my p prime. But I'm assuming p is positive, okay? So I will erase this here. Now my equilibrium solution, are p equals 0 and p equal to k. Okay. So these are the equilibrium solution. Remember, these are solution, okay? So if I start with a population equal k, it will stay k. If I start a population equal 0, it will stay 0, okay? Let's say if p of t0, is bigger than k, which means I'm starting with a point here, okay? Then, or if I want to write here, this is the point here, okay? Then I have p prime is negative. P prime is negative means P is decreasing, which means it will move to the left on my curve. Move to the left means it will go up on my curve, but it will go up mean P prime is increasing, but when P prime is increasing, P double derivative is positive and P is concave up. So I imagine a solution that is decreasing and concave up. Okay. So I expect it will go, but it will never get to K because solution cannot intersect. So the limit as t goes to infinity of P of t is K. Now if P of t0 smaller than K, so let's say I'm somewhere here. Okay. Then P prime is positive. Yes, I mean if it means P prime is positive, but if P prime is positive mean P is increasing. But if P increase, it means I'm going to the left. But I'm going to the left, it depends if my point was here or if my point was here. But going to the left because here means I'm going up, going to the left here means going down. So this is two cases, which means if P of t, if I have P between 0 and K over 2, what do I have? I have P is increasing mean P prime, so I'm here on this blue line. I'm going to the left mean I'm going up, mean P prime is increasing, which means P double second is positive, which means P is concave up. What if P is between, no, this is K over 2 to K. Sorry, I'm between K over 2 and K. What if P between 0 and K over 2? What if I am on this interval? If I am on this interval, I do something wrong. I did something wrong. So let's erase this, and let's re-explain. Remove this, sorry about that. Okay. P is increasing. Again, P is increasing mean I'm going right, not left. P is increasing mean I'm going right. But if I'm here going right mean go down, and if I'm here going right means go up. So this depends on two things. If P is between K over 2 and K, this means P is increasing mean P prime, since I'm going to the right, means P prime is going down. So, means the arrow is going down, which means P prime is decreasing. But if P prime is decreasing, P second is negative, so it's concave down. Now, if P is between 0 and K over 2, means P prime is going up. Why? P prime is increasing because when I go to the right, the arrow goes up. This means P second is positive and concave up. So P is concave up, P is concave up. And I have that the limit as t goes to infinity of P of t is equal to K. Then this will be, but then where it will change, notice that we have an inflection point whenever the population reaches K over 2. Because this is, before it was concave up, and after it is concave down. Let's explain what happened here. So at K over 2, I have something. And here is, first of all, it started concave up, and then it flattens. It goes up, and then it flattens at K over 2. So it starts with an exponential growth and then it flattens the curve, and this is exactly what we have been talking about in the news all this time. Okay. Remember, it will never go to the, this should have been in yellow, it will never intersect any other solution. So I expect the limit as t goes to infinity to be k. So the limit as t goes to infinity of p of t is k. Okay, so this is k is the maximum capacity of the population. It's the equilibrium capacity. So what kind of equilibrium? Is it a stable equilibrium or not? You see the arrows are going in both of these cases toward k. So p of t equal k is an attractor. So we can say it's a stable equilibrium solution. What about p of t equals 0? This is another equilibrium solution. Let's forget what is my model. So let's say it's not a population. My solution is allowed to be negative. So I will make it like this. Okay. I will allow p to be negative. So this will be p, this will be t, and I will allow negative, this will be p prime, so this will be p, and this is an equilibrium solution. We used to do it in which color? Sorry, in green. Okay, so if I am here, I did this way. You see it? It's the same one. What if I am at this part of my curve? If I'm on this part of the curve, I have p prime is negative, which means p is decreasing. P is decreasing means I'm going to the left. P is decreasing means going to the left, so p is decreasing, and then this implies that p prime is decreasing concave down, p is concave down. I mean, I'm giving you all information, monotonicity, concavity, p is concave down, and if p is concave down, then, I mean, okay, then you can see two arrows are going away from the equilibrium solution. So this is a non-stable, so 0 is non-stable or unstable, and it's static pressure. Okay. Now last, something about this model, say probabilistic equation with hunting. Yes, I'm allowing hunting. Let's say I have p prime equal rp into 1 minus p over k, and then minus h. Okay, and then there's a big exercise in the there's a large exercise in the what do we say, in not in the recitation, in the problem set, where it tells you that if I'm allowing hunting, if I allow hunting, what happened? Can I allow hunting, and which rate, without the population together go extinct, and at which rate we can hunt so that the population stay safe. But let's say, so C problem set, but let's study the case where p prime equal rp to 1 minus p over k minus k over 2, which means h equal k over 2. So this was my original one. This is p prime, and this is p. This is my original one. This is when h equals 0, and this was k over 2. No, not h equal k over 2. So when p equal k over 2, r p prime was what? Equal r k over 2 into 1 minus k over 2, correct? Over k, which means rk over 4. So let's say H is RK over 4. In fact, this is how, so this will be RK over 4. This one, when H equals 0, when H equals RK over 4, this will go down by RK over 4, and we will get the following. So this is RK over 4, but now I let H to be RK over 4, so I have minus H, so I will go down RK over 4, and you will get the following graph. Now what is the equilibrium solution in this case? This is my equilibrium solution. Now the question is it stable or unstable? Okay, let's start. If P at T0 is bigger than K over 2. So let's say I start at some point here. I just need to know it's stable or not. I don't need concavity or anything. So this means my P prime will be negative, which means my P will be decreasing, correct? But if my P is decreasing, mean I will have to go to the left, correct? Which means I have to go to the left. But if I have to go to the left, mean I have to go up, which means P prime will be increasing, okay? So I go up. What if P of T0 is smaller than K over 2? So it looks like an attractor, yes? But let's check if this is correct. If it's smaller than K over 2, then my P prime is what? Is also negative. So my P is decreasing. So also I have to go to the left. This is strange. I have to go to the left, so P prime is decreasing. So this means from this side, if I start this initial condition, I have a repellent, and from this side, I have an attractor. So we call this now, this is not stable, not unstable, we call it semi-stable. Okay? This is called semi-stable equilibrium solution. And then I covered all the cases with modeling. You don't have to have a model, by the way, to work on. You can start with an any autonomous ODE and study all these